So the next speaker is Ji-Yu Hyun, and she's from EPFL. So she was born in Seoul, Korea. She has received the Bachelor of Science in Electrical and Electronic Engineering from Yonsei University in 2015. She received the Master of Science in Electrical Engineering from the National University of Seoul in 2018. And she's currently a PhD student at the Distributed Electrical Systems Laboratory at the Swiss Federal Institute of Technology of Lausanne, EPFL. And her research interests include distribution system planning for procurement of local system flexibility. Thank you, Ji. The floor is yours, and good luck with your presentation.
Thank you, Fabrizio, for introduction. Hello, my name is Ji-Hyun Lee.
Ji, sorry to interrupt you. Yeah,
share screen.
Remember to share the screen. Thank you.
This one. Yeah, okay. Yeah, you see my screen?
Yes, I do. Thank you.
Okay. Hello, my name is Ji-Hyun Lee, a PhD student working in Distributed Electrical Systems Laboratory in EPFL. The title of the presentation is Dispatch-Aware Planning of Energy Storage Systems in Active Distribution Networks. Okay. Sorry.
Yes.
Okay. Distributed renewable energy resources. Hereafter, I would call it DRER. Penetration is increasing with a large part connected to distribution systems. Due to the increasing DRER, several operational challenges are brought to the DSO, such as decrease in quality of supply voltage and increased congestion in line, and increased variability in consumption, and the decrease in accuracy of the power scheduling and controllability of operating point. The energy storage systems can be exploited by DSOs to cope with each of these challenges by controlling the nodal voltages, line congestions, or offering service of peak shaving or load shifting. And on top of that, I would like to focus today on the last one on the list, which is to achieve dispatchability to cope with the uncertainty of consumption. The ADNs operated by DSOs are linked to the grid operated by TSO via grid connecting point, so-called GCP. High DRER penetration incurs difficulty in predicting the consumption within the ADNs, causing the deviation in the power flow realization from the day-ahead power schedule on the GCP. And then accumulated imbalance requires large amount of spinning reserve for TSOs to maintain system balance. And therefore, there has been several studies calling for the sharing the imbalance responsibility between TSOs and DSOs. And moreover, there has been also the increase in responsibility, suggesting the increase in responsibility for DSOs to mitigate the imbalance caused within its own ADN. In this way, the DSO can be exposed to the high risk to pay large amount of penalty costs due to the imbalance within the ADNs. With this respect, we propose to achieve dispatched by design distributed system with optimal allocation of ESS that can assure the distribution feeder to follow the computed power schedules, and thereby the DSO can mitigate the imbalance cost. First, let's have a look at the definition of the dispatchability. The active power flow at the GCP consists of consumption and the grid losses over all nodes within the network. Due to the prediction uncertainty, the consumption at each node deviates from each prediction points as well as the line losses. Therefore, we express the consumption and the grid losses by prediction and deviation. The dispatch plan denotes the predefined schedule of active power flow at the GCP that the feeder should follow. It is determined based on the sum of the offset profile of each ESS and the aggregated consumption prediction considering the grid losses. The power mismatch between the dispatch plan and the realized active power at the GCP can be indicated as the left side of this equation. And the mismatch can divide, and we can divide this value into two terms. Mismatch covered by the ESS and the leftover mismatch, which would be observed as dispatch error at GCP. In order to enhance the dispatchability, the ESS control strategy is designed to maximize the exploitation of the ESS capacity for compensating the uncertainty due to the stochastic nature of the resources, while complying with the ESS energy and power operating constraints. The control term is defined as offset profile, which is assigned to each of the allocated ESS, as shown in the expression here. The offset profile adjusts the ESS active power with the objective of restoring an adequate ESS state of energy, such that during operation, enough up and down flexibility is available to compensate the mismatch between the prediction and the realization of the presumption. The offset profile is embedded to the operation of ADN by simply adding the offset profile to the dispatch plan, along with the presumption prediction. As we solve an optimization problem to minimize the dispatch error for the operation horizon, along with the summed magnitude of the offset profile, of course, while subjected to the network constraints and also the ESS-related constraints, we can determine the dispatchability of ADNs by the total magnitude of dispatch error for the operation horizon. The proposed ESS planning is defined by formulating and solving a scenario-based optimal power flow. The equations of full AC OPF are given in the slides, and the original OPF is nonlinear and non-convex due to the constraints colored in pink here. So in order to convexify it, it is converted to a piecewise linearized OPF. And I would call it, in short, PWL OPF from now on. We chose to implement the PWL OPF because the method is widely used in tackling various research interests in power system, thanks to its flexibility of implementation. Also, it can achieve the optimal solution of reasonable quality with minor approximation error from the original OPF solution. In PWL OPF, we linearized the nonlinear term within the power flow equations and constraints. First, we replaced the nodal voltage variable with the voltage lower bound value. Then we apply the piecewise linearization function to all the quadratic terms, which are upstream complex power flow to the line and downstream complex power flow on line, and also the line longitudinal reactive power. The piecewise linearization approximation is illustrated with the graph on the right side. Please note that the accuracy of the approximation highly depends on the number of discretization, which is shown here as gamma, and also the maximum possible value of each term. The planning problem is formulated into a stochastic two-stage optimization problem. In the first stage optimization, investment decisions including ESS installation, energy reservoir, and power ratings are determined. And the presumption uncertainty is realized in the second stage optimization as operating scenarios. In the second stage, considering different operative scenarios, the ESS contribution is assessed based on OPF model, taking operational decisions such as offset profile and ESS dispatch regarding the dispatchability of ADN. When the optimal solution is obtained both from the first stage and the second stage through iterative process, the global optimal solution is obtained. More specifically, we present a two-stage procedure for the optimal siting and sizing of ESS, considering the control strategy of ESS. To tackle the computational complexity of the proposed planning problem, we decompose into two problems by applying Bender's decomposition technique. The first is the master problem, which corresponds to the first stage optimization problem, which I explained on the former slide. And the second, and the subproblem, which is equivalent to the second stage optimization problem. In the master problem, we determine the ESS allocation with the objective of minimizing the investment cost of ESS, which comprise the fixed cost, power rating cost, and energy reservoir cost. And also the approximated subproblem cost should be added. The constraints are grouped as the investment constraints and the costs for the Bender's algorithm. Investment constraints includes the possible power rating range and the energy reservoir range, and also the maximum power that can be discharged or charged relative to the maximum capacity. For the Bender's cuts, there should be an initial cut which actually lower bounds the subproblem cost on the initial stage, and then the Bender's cuts gets to be added with each of the iteration of Bender's algorithm. And when the master problem is solved, we can calculate the lower bound of the total cost from the optimal solution, and we'll call it LB here. The subproblem evaluates the system operational condition regarding the dispatchability while determining operational decisions to control the ESS and the grid. The objective is defined as minimization of offset profile, dispatch error, and the total grid losses. The constraints includes the modeling of the dispatchability and also the PWL OPF equations, including the operating constraints regarding the nodal voltage and the line opacity. All of these equations have been discussed in detail in former slides. Moreover, the ESS operational characteristics such as ESS capability curve and dynamic SOE level modeling, and also SOE range constraints should be implemented. And also, for the last part, the ESS size are fixed in the subproblem to the master problem solution. And we obtain the dual values from here in this constraint so that we can build up the Bender's cuts for the next iteration. After the subproblem is solved, upper bound or UB is obtained by adding the subproblem cost to the cost got from the master problem. And the difference between the upper bound and the lower bound is checked. If the difference is bigger than the tolerance, the dual values got from the subproblem, we generate the Bender's cuts with using the dual values and the subproblem cost, and we resolve the master problem. And after a certain number of iterations, as the difference between the UB and LB gets lower than the tolerance, the optimal solution is finally obtained. To verify the effectiveness of the ESS control scheme, we demonstrate the simulation on a real Swiss grid consists of 55 buses located in Aigle. Planning horizon is set as 10 years. The peak consumption is 3.6 megawatts and PV capacity is 2.7 megawatts peak. And the hydropower capacity is 805 kilovolt ampere in the network. In order to reflect seasonal variation in consumption, we chose 8 day types. For modeling the prediction uncertainty, we generated 1,000 scenarios, and then for each day type, and then we reduced to 10 scenarios using K-Meadows clustering scenario reduction. The specification on the ESS cost and the candidate notes are given in the table, along with the imbalance penalty price, which is set to be very high compared to the real energy market value price in order to reach the sufficient level of dispatchability. We conducted the simulation based on 3 cases, with no ESS allocation, and with ESS allocation also with the embedded with the control strategy. And also the last case should be the ESS allocation, but without the control strategy. And this is the result of the allocation. At note 4, both of ESS energy reservoirs and power ratings are bigger in case one. In case one, than in case two, or whereas at the note 27, the energy reservoir is bigger in case one, but the power ratings are similar in both cases. But overall investment cost is $0.15 million larger in case one, and the annual uncovered dispatch error is lower in case one with 51.7 megawatt hour. And this leads to the reduction of $0.2 million in the total cost for the case one compared to the case two. And this difference in allocation and the dispatch results can be associated with the efficiency of the ESS control scheme. The operational advantage of the ESS allocation and the superiority of the case one over case two are visualized in the graph showing the dispatch results for the day type one, including the presumption prediction and dispatch plan, and also the active power flow through the GCP for each of the scenarios. Without the support of ESS, the DSO is expected to pay a high penalty cost due to the prediction error, especially during the daytime, where a lot of uncertainty is shown here. Meanwhile, when the ESS is allocated, the ESS effectively reduces the possible dispatch error by 98%. The difference in case one and case two is shown in the dispatch plan. The dispatch plan in case one deviates from the total presumption prediction, which is shown as a red line, in the time intervals where the offset profile takes value. And this is when, due to the high prediction error of PV generation, the large amount of dispatch error at the GCP is anticipated at the following time intervals. Thanks to the offset profile, the utilization of the energy reservoir capacity of each dispatch interval can be optimized, considering up to the dispatch error anticipated in upcoming intervals. So to summarize, this paper proposed a procedure for the optimal siting and sizing of ESS within the ADNs hosting a large amount of DRER. And the ESS control strategy is integrated to fully exploit the energy capacity of the ESS for the compensation of the dispatch error. The allocation of ESS planning is defined by formulating and solving a scenario-based OPF, which is then convexified and linearized as PWL OPF model. Then, in order to tackle the computational complexity of the proposed planning problem, we employed the Bender's decomposition technique. The simulation on a real Swiss grid shows that the ESS allocation based on the proposed method can achieve the dispatchability of ADNs. Well, thank you very much.
Okay, thank you. Thanks, Jim. Thank you for a very good presentation. So we have a few questions from the audience. So I'll start with this one. Jordan Auberger is asking for a clarification and is asking what does energy storage systems do without a control strategy? How the batteries have been used in this case? So I think in your presentation, yeah, you had case one and case two, and I think in case two or case one, it was without control strategy. So what batteries, what the batteries are doing there?
Can you repeat the question? Sorry.
So in your presentation, I think at some point you had the case one and case two, and one of the cases was referring to the case where the BSS were controlled without any, were essentially without control strategy.
Okay.
So yeah, what batteries are doing in this case?
Oh, so
yeah, case two, yes, yeah. This
so
one,
comparing the case one and case two.
Yeah, exactly.
Yeah. So
yeah,
in the case, yeah. So in the case one, the control strategy of the ESS is embedded with the term of offset profile, as I shown in the former slides. And so this actually, the offset profile adjusts the bias. It biases the the power flow through the GCP so that it can adjust the level of SOE in the ESS. And this leveling, this adjusting of the SOE level can make the ESS to be get ready for the, what do you say, the anticipated the dispatch error in upcoming intervals, so that it can, so it can have more flexibility within the SOE. And this actually makes the ESS to be more flexible, to have more, to compensate the dispatch error more than the without the case without the offset profile.
Okay, right. Thank you. So we just take 2 more questions. I apologize. There are many questions, and I apologize with the audience. I will just pick randomly among those that seems more like maybe more conducive to an interesting discussion. So Matt Salki is asking, is first of all congratulating with you for a good presentation, and is asking essentially, what do you expect is the impact on a free-phase grid? So at the current stage, you're considering a single phase power flow. How do you think results could be impacted by a free-phase load flow?
Yeah, currently, yeah, thank you for the thank you for the question. And currently, I am implementing just a single phase formulation, but this can be easily implemented to 3-phase as well, by because this is based on the modeling of a branch flow model, and this can be also changed to the 3-phase.
Okay, so it's something that it can be done. Okay, thank you. And the last question that I will take is from Garrett Gill. And Garrett Gill is saying that there is evidence to suggest that Bender's decomposition does not scale well with larger networks. Are there any plans to apply this method to bigger networks?
Actually, Bender's decomposition Bender's decomposition, the advantage of Bender's decomposition is that it can scale up to the big network as well. So I think the advantage of Bender's decomposition is that it can really scale up to the bigger problem. But I haven't tried up to like more than 100 nodes still. But I think it's
which, however, for distribution systems is a good size.
Yeah. So yeah.
Okay, thank you very much. Maybe there are a few other questions, so I encourage you to use the question and answer panel and type maybe an answer if you want directly there. And this, I extend also the same invite to Louis. So Louis was the 3rd presenter. There are a few still pending questions in the Q&A panel. So if you guys want to, if the authors want to interact with the audience, they can by typing an answer directly there. So we now pass to the last presentation because we are maybe 5 minutes late. Thank you, G, for a nice presentation.